SpaceX has offered $60 billion to acquire a text editor. The valuation has climbed from $2.5 billion to $60 billion in only 15 months. This acquisition allows SpaceX to vertically integrate the global software development stack, effectively seizing control of how all future code is written. Cursor operates without a proprietary foundational model, instead utilizing the same Claude and GPT-4o APIs available to any individual developer. The system's performance relies on a local retrieval-augmented generation pipeline designed to navigate repository data more efficiently than a standard context window. SpaceX is paying for data orchestration and the strategic control of the developer interface. The AI stack has 3 layers. The bottom is infrastructure, raw GPUs, and compute. The middle contains foundational models, competing on price. The top is the developer interface, the critical touchpoint controlling workflows and capturing all engineering data. As foundational models become commodities, the interface layer becomes the primary operating system for global software engineering. Even the largest language models face a severe physical limitation when processing a production-scale software repository containing 50,000 files. Feeding raw code into these models leads to hallucinations or the loss of essential project dependencies. Cursor addresses this by using TreeSitter to parse code as an abstract syntax tree. This organizes the code into a hierarchy of parent and child nodes, breaking the codebase into intact logical units, such as specific functions. Structural parsing ensures the AI receives complete functional thoughts rather than fragmented strings of text. Maintaining a continuous index of a constantly changing repository requires extreme local computing efficiency to avoid slowing down the developer's machine. Cursor utilizes Merkle trees to index projects, assigning unique cryptographic hashes to every file and folder. Each possesses a fingerprint, updating based on contents below. When editing a line, only that hash changes, updating the root while leaving the rest untouched. This hashing architecture allows the system to map repository changes locally, bypassing the need to re-index the entire project. Keyword searches often fail to find related logic across different files. A search for login will miss a file named authenticate.ts, even if the functionality is identical. Cursor uses the TurboPuffer database to convert code chunks into high-dimensional vector embeddings. These map semantic meaning, placing authentication and payment logic into different quadrants based on purpose. When requesting a refactor, the prompt itself becomes a vector to find nearest semantic matches. Through agentic tracing, Cursor follows the import graph to identify dependencies, callers, and middleware connected to that logic. Raw source code remains on the local machine. The system only sends obfuscated vectors and focused briefs to the external AI model. Cursor acts as an active orchestrator, compiling hyper-focused briefs that expand the underlying model's effective context. This local architecture is the foundation for the broader corporate strategy shared by xAI and Cursor. Currently, xAI's Grok models have limited traction in the agentic coding market compared to competitors like Claude. Major firms, including NVIDIA and Stripe, already pay for Cursor, which is currently used by over half of the Fortune 500. Acquiring the company gives SpaceX direct access to these daily engineering workflows. This strategic move pairs xAI's bare metal hardware with a dominant developer interface. Owning the interface provides a defensible moat as foundational models increasingly compete on price. The $60 billion valuation represents a strategic investment to own the distribution and the routing system of the AI engineering sector. This integration positions the upcoming SpaceX IPO as a full-stack AI platform rather than a specialized aerospace company. For developers, utilizing this pipeline requires moving away from keyword-based habits and towards semantic search. Effective use of the system involves setting explicit repository rules, constraining agent scopes, and designing prompts that leverage semantic retrieval. The tool operates as a dependency tracing copilot that remains dependent on the structural integrity of the codebase it indexes. The strategic focus has moved from model parameter counts to the architectural interface where software is actually deployed.